Okay, in chapter 23, we looked at the laws of optics dealing with lenses and mirrors and saw how the focal length is related to the object and image distances and so forth. Well, in chapter 25, we're going to apply that physics to some specific optical instruments and see how it works. We're going to start out with the human eye, our most familiar optical instrument. And this is a very busy image. You don't really need to know most of these terms, but I just wanted to point out the basics here. The human eye is basically a spherical little box, sort of like a camera. It's got a lens on one side, and it's got the sensitive material called the retina on the back. That's where the image is actually formed. Notice that the lens is surrounded by little muscles. Those muscles can squeeze the lens and change its shape and actually change its focal length a little bit, depending on how far away the object is that you're looking at. Notice this blue stuff. This is your iris, the colored part of your eye, with the black pupil in the middle. The pupil is where the light actually goes into. Now, if there's too much light, if you're in a really bright sunlight or snowy beachscape situation, you've got too much light going, it's too bright, it might damage your retina. What happens is that the iris actually changes the shape of the pupil. The pupil contracts and becomes smaller to cut out some of the light. If you're in a dark situation, in a darkened room or at night, the pupil expands, the iris pulls back and allows more light to go through the pupil. In front of the eye, we have this horny shell type material that's transparent. It's called the cornea. It's filled with the fluid. That's actually where most of the light bends and most of the focusing is actually done. So that's the basic anatomy of the human eye. Here's a couple of images taken from the movie E.T. just to show you what we were talking about in the previous frame, where if there's too much light, your pupil constricts. This is just a puppet, this alien creature, but they went to great pains to make it realistic. If you notice in the left-hand picture, look at the black pupils in the middle of the eye, how big they are, because the creature's in a sort of a dark room at first before his finger lights up. But when his finger lights up to heal a cut in the finger of the child actor, notice in the right-hand side, the pupils have gotten smaller. They've actually constricted. This is done, of course, as a special effect mechanically, but that actually is what happens with human eyes when the light level changes. You can experience this yourself. If you go into the bathroom and turn out the lights, make it nice and dark, and stay there for about half a minute. Look into the mirror at your face, and as you turn the lights on, look at your eyes, and you will see the pupils of your eyes constrict to protect your retina from too much light coming through. Most of the people who saw this movie probably didn't notice the pupil constricting when it happened, but it added realism at the subconscious level. Okay, before we get into how the eye actually focuses on objects of changing distance, let's remind ourselves the optics of the situation with just a simple lens. In the top image, you see an object at the left at a distance p, the image formed on the right at a distance q. On the bottom image, you see the object has come in closer. Notice that the image has gone out farther away. So as p gets smaller, q gets bigger. That's just according to 1 over f equals 1 over p plus 1 over q. So how does the human eye deal with this situation? As an object gets closer to the eye, the image is going to move farther away. How does the eye deal with that? Now with a camera, when the object gets closer and the image gets farther away, the lens is just moved out to make the image come back into the film. But the human eye is quite different. Notice in the top image we have an object that's supposedly far away, almost like infinitely far away. The light is coming in parallel, goes through the lens in the top image there, and comes to a focus on the retina. In the bottom image, you see the object has come closer, so you would expect the image to be farther out towards the right. But notice that it's focused on the retina because look at the lens. the lens is fatter on the bottom because the muscles are squeezing it to change the focal length. So even though the object would make an image beyond the retina on the right-hand side, the lens shortens its focal length and brings the image into the retina just by those little muscles. That's why your eyes can actually get tired when you're doing a lot of reading or a lot of screen viewing and you're focusing on things close up for hours and hours. Those little muscles can become tired. That's why it's recommended that every once in a while you look out a window at some distant trees or houses or mountains or something to allow those little muscles to relax a little bit. Okay, here's how it works with a normal eye. On the top view, you've got a relaxed eye. The muscles are not squeezing the lens. You've got the object as distance. With a normal eye, for a distant object, the image will focus right on the retina. As you bring the object closer, you see in the second image down there, the object coming closer, you can see that the image wants to be farther out beyond the retina, so it wouldn't be in focus. That would be if the eye was still relaxed. In the third image, you can see when the eye accommodates, when those little muscles begin to squeeze the lens to change the focal length and bring that image back under the retina so it's focused, that's called accommodation. The eye is working now, the muscles are working to bring that image onto the retina and keep it focused. The normal near object distance of focusing is about 25 centimeters for the normal human eye. Now in the bottom image, you get the object too close to your eye has already accommodated, the muscles have squeezed the lens as much as they can, and so now when the image moves even farther out, your eye isn't capable of bringing it back onto the retina because the eye is already accommodated as much as it can. Now there are two common eye problems that can be corrected by wearing glasses or contacts. One of these problems is called hyperopia, which is farsightedness. And here's how it works. Notice that the eyeball is a little bit squashed, a little bit flattened. People who have an eyeball that's a little bit too short, when they look at something far away like a mountain, the object is distant, and the lens is focusing the object into an image. You can see in the top picture, the image on the right is beyond the retina. Why? Because the eyeball is a little too short, so it misses. So when the eye is relaxed and they're looking at a distant object, it's out of focus because the image is beyond the retina. But in this case, the eye can accommodate, the little muscles squeeze the lens and bring that image onto the retina so it can be in focus. So this person can see distant objects, but they have to work at it to see it. The eye has to accommodate in order to bring that image onto the retina. Now, if you bring the object even closer to the normal near point of about 25 centimeters for most people, notice that the image moves farther out, but now the lens can't bring it onto the retina because it's already accommodated. And so this person can't see things that are at the normal near point of 25 centimeters. They can see far away things, but they can't see at a normal near distance. So this can be corrected by putting a converging lens in front of the eye. And that lens brings that image, as you can see in the bottom picture, brings that image that was beyond the retina, brings it onto the retina so now it's in focus. So hyperopia, farsightedness, can be corrected by a converging lens that allows people to see things at the normal near point, about 25 centimeters. The other problem that could be corrected by glasses is myopia, or nearsightedness. It's just the opposite problem from hyperopia. Notice in the top picture there, the eyeball is a little bit too long. So an object that is very distant makes an image inside the eye, but it's not on the retina because the eyeball is a little bit too long. So in this case, if the person tries to accommodate, that would just bring the image even closer to the left, which is farther from the retina. It wouldn't help them to see the object that's distant. Now, if you bring the object in the second picture, if you bring the object closer, like to 25 centimeters, Notice that the image moves farther out. Now the image is on the back of the eye, on the retina, and the eye isn't even accommodated. It's still relaxed. So that person can easily see things at the normal near point of 25 centimeters. Now, if you bring the object even closer, let's say for example 15 centimeters, now the image would want to move farther out beyond the retina, but now the eye can accommodate, it still has that accommodation ability to bring the image onto the retina, and so they can still see it in focus. So a myopic person can see things closer than most normal people because their eyeball is elongated and their eye can accommodate to bring the image to the retina. Notice though, they can't see things that are far away as the top image shows. In the bottom image, this is corrected by a diverging lens. Notice in the top image, the top picture, the image is too close, it's off the retina, but on the bottom image, the diverging lens moves it back so that image is now on the retina and the image is now in focus. So for hyperopia, which is farsightedness, the eye can't see things that are near. Say 25 centimeters is the normal near point, and if you put an object 25 centimeters from a hyperopic eye, it can't focus it, as in the top image. An eye like that might have a near point of 40 centimeters or some other number, but for example, if this eye has a near point of 40 centimeters, it means it can't see anything closer than 40 centimeters. So what we need is a lens that will make an image of the object when the object is at 25 centimeters to make an image of the object farther away, say at 40 centimeters, like the bottom picture shows. That would be the converging lens. So in a problem like this, you might be given the focal length of the lens, the object distance, and be asked to find where the image would be formed. More likely, you would be given the person's near point, which would be Q. In this case is -4 centimeters because you're looking through the lens at a virtual image. And you want to be able to hold it at the normal near point, 25 centimeters. You want the image to be farther back at 40 centimeters. Then you would just plug those numbers, the P and Q, into the formula as seen in the bottom. So just be sure the Q is negative because you're looking through the lens. So the myopic eye, the nearsighted eye, remember, is elongated so that when an object is very distant, the image is formed in front of the retina, so it's out of focus. So what's needed is the diverging lens that you can see in the lower picture, so that when the object is distant, that is a P of infinity, object distance very far away, you want the lens to bring the image into where he can see it at the eye's far point. In this case, let's take the far point to be 15 meters, which means that you can't see anything in focus that's farther than 15 meters away. So by putting the diverging lens in front of the eye, it takes an object at infinity, makes an image of it 15 meters in front of the eye. So in this case, P would be infinity, Q would be -15 meters because you're looking through the lens at a virtual image. And those are the numbers that you would plug into the formula to find the focal length of the lens. One more thing to mention is that the opticians, the people who actually prescribe the lenses for your glasses, they don't usually speak in terms of the focal length of the lenses they're prescribing. They have their own language. They use what's called power, the power of the lens, and it's measured in diopters. It's just equal to the reciprocal of the focal length. I guess in the formula, you know, it's 1 over f equals 1 over p plus 1. I guess it's easier. Instead of having to take the reciprocal at the end to get the focal length, you just keep it 1 over f and call it power in diopters. So if you ever go to Rite Aid or Walgreens or someplace looking for a pair of reading glasses, they're all rated in diopters. Another optical instrument we can look at using the laws of optics that we've studied so far is the simple magnifying lens. When you want to look carefully at something small, you naturally bring it closer to your eye so you can see it better, but you can't bring it closer than about 25 centimeters without getting it out of focus. So what the magnifying lens does, it allows you to bring it closer so it looks bigger. It doesn't actually make a bigger image, it just lets you look at it more closer up. The actual magnifying power of the lens can vary depending on where you hold the object. There's a range of object positions that'll provide a focused view. Holding the lens in front of your eye and the object in front of the lens, if you pull the object farther away, you reach the farthest position where it'll be in focus. In this position, the image will be at infinity, and your eye will therefore be relaxed. The magnifying power at this point will be the one shown in the first equation below, just 25 centimeters divided by the focal length of the lens. It's possible to bring the object closer to the lens, but the image will also be closer and a little bit bigger, so your eye will have to accommodate. The closest it can come gives a magnifying power which is greater than the object when it's farther, but the eye has to work a little bit to see it. The magnification, as you can see in the bottom equation, is just 25 divided by the focal length of the lens plus 1. The same as before, but just with a 1 added to it. So if the magnifying power for the relaxed eye is, say, 3 power, then if you bring it closer to the lens, you can get 4 power. Another optical instrument we can look at, slightly more complicated than the magnifying glass, is the telescope. Amazingly, you can build a telescope with only 2 lenses. One of the lenses, the one you put in front of your eye and look through, that's the eyepiece. The other is a bigger lens that you put out in front of the eyepiece. That's called the objective lens. Here's how it works. Say you're looking at a distant tree or the moon or something. The light from that object comes through the objective lens and focuses it at the focal point of the objective lens. You can see there in the diagram the objective focus. What the lens does is it makes an image of that distant object, a little upside down inverted image at the focal point of the lens. That image is a real image. There's actually light passing through it, and it's actually sort of like hanging there in space. And all the eyepiece does, it acts like a magnifying glass, and you look through it at that little image. If that was your thumb, you'd be looking at the eyepiece, the magnifying glass, that's your thumb. But here you're looking at the image formed by the objective lens. And that makes a greatly enlarged image which you can examine through the eyepiece. To find the magnifying power of a telescope is very simple. You can see the formula at the bottom. Magnifying power M is just equal to the focal length of the objective lens divided by the focal length of the eyepiece. So the longer the focal length of the objective, the greater the magnifying power you'll have. But the shorter the focal length of the eyepiece, that will increase the magnifying power. So you want the objective to have a long focal length and the eyepiece to have a short focal length. And that'll increase the magnifying power of your telescope. The derivation of this is given in your book. It's very simple. I recommend that you look through it. The telescope we were just looking at is called a refracting telescope because it uses a lens for the objective. There's another kind of telescope called a reflecting telescope that uses a mirror. It was invented by Isaac Newton. You can see in this diagram here, when the light comes in from the left, instead of passing through a lens, it strikes that concave mirror there, and that mirror focuses the light. Now, if we were trying to stick our head in there and look at it, we would block the light. So the clever part of this telescope is that little secondary mirror there you see in the middle, which reflects the light out through the side of the telescope, and that's where you put your eyepiece. So the image is actually formed through the eyepiece into your eye. The advantage of this telescope is that instead of using a lens, the lens, when light passes through glass like a prism, it breaks the light up into colors a little bit, called chromatic aberration. Well, this telescope doesn't do that. So it's free of chromatic aberration, and it has many other benefits. All major telescopes in the world today are reflecting telescopes as opposed to refracting telescopes. Now, to make a microscope like a telescope, you need only two lenses in its basic form. The one lens being the eyepiece, which is what you hold up to your eye. The other one is the objective that collects the light, just like with a telescope. Except with a microscope, instead of trying to look at something far away, we're trying to look at something very tiny close up. So notice in this diagram, you can see the focal length of the objective over on the left-hand side, that FO. That's the focal length of the objective lens. And notice how they've placed the object very close to that focal length. Now remember from before, as you bring the object closer to the lens, the image is projected farther away. So with the object being very close to the lens, the image is projected very far away and becomes very big. The farther away it goes, the bigger it gets. So that's the basic principle for the magnifying power of the microscope. Then, once the objective produces the real image there hanging in space, you can look through the eyepiece just like a magnifying glass to make it look even bigger. So the formula for calculating the magnifying power of the microscope, you can see at the bottom there. It involves not only the focal lengths of the two lenses, but also the distance between them, L. And you can calculate that magnifying power just by dividing L by focal length of the objective times 25 centimeters over the focal length of the eyepiece, where all the distances are expressed in centimeters. Notice also there's a negative sign in front of the formula. That just means you're looking through the eyepiece, so the final image you see is a virtual image. Okay, there's one more thing we need to consider when talking about the power of a telescope. There's something called the resolving power of the telescope. Remember when we were talking about diffraction of slits? The narrower the slit, the greater the diffraction, the wider the slit, the less the diffraction. Well, the same thing is true of telescopes. Notice that the telescope you see here on the upper right has an aperture. That's just the size of the opening for the light to come through. And it turns out it follows the same principle as the narrow and wide slits. The smaller the aperture, that is, the smaller the diameter of the objective, the bigger the diffraction pattern you get at. Now, when you take an image of a star in the sky, notice the lower right-hand image there. It doesn't turn out to be a pinpoint of light the way it really is. It gets diffracted. As the light goes through the aperture of the telescope, it becomes diffracted into this diffraction pattern. You see the diffracted star image there. And the general principle is the smaller the telescope, the smaller the aperture, the bigger that diffraction pattern is going to be. And the wider the aperture, the smaller the diffraction pattern. And you want it to be small. You want it to be, it's really basically just a pinpoint of light. So you want that diffraction pattern to be small, which means you want the aperture to be big, which is why all the major telescopes of the world today have large objective mirrors to reduce the diffraction of the star images. Okay, so here's the deal. Suppose you want to look at two stars in the sky, only they're really close together. In the lower right-hand image there, you see two little circles. Those represent the stars in the sky. The aperture there on the left represents the telescope aperture or diameter of the objective. R is the distance of the stars from the telescope. And theta is the angle, the apparent angle between those two stars. S is the actual linear distance between the two stars. The question is, how close together can they be and have you still see them as two stars? You see, just to the left of the aperture in the lower right-hand image, you see those two little red circles? Those represents the diffraction patterns. So the stars don't show up as just points of light. They show up as diffraction patterns because as the light passes through the telescope aperture, it gets diffracted or smeared out. So you see those two smeared circles. Those are the diffraction patterns of the stars. Now, if you come up here, oh man, I could have been using this. Shift. Okay, so this image down here in the lower right, this represents two stars, these two little circles here, a distance r from a telescope opening. This gap here represents the aperture or the diameter of the telescope that's looking at these two stars. The problem is the light coming from these two stars doesn't show up as a pinpoint of light, which they really are. They get diffracted and smeared out into this diffraction pattern. Now, if you have two stars, then you're going to have two diffraction patterns. Now, if these two stars are really close together in the sky, the question is how close can they be, and have you still see them as two stars? You see, up here in the upper image on the right-hand side, if they're too close together, see that these graphs represent the diffraction patterns of the two stars. And those two stars are so close together, their diffraction patterns overlap. And so you can't really tell there's two stars there. You can't resolve them or separate them into two stars. The other extreme is over on the left. They're far apart enough that you can clearly distinguish them as two different stars, two different diffraction patterns. So the question is, how close together can they be and still be resolved? Well, this central image is the criterion here. Notice that the diffraction pattern for one star has a maximum and a first minimum. The diffraction pattern for the second star has a maximum and a first minimum. So the criterion for resolving the stars is this. If the minimum of one diffraction pattern is in the same position as the maximum of the other, then we can say they are just barely resolved. They're just resolved. So that's the point at which you can tell there's two stars and not just one. The formula for this is theta minimum, the smallest angle that you can have and resolve the stars. Theta minimum is just 1.22 times the wavelength of the light divided by d, which is the aperture of the telescope, the diameter of the objective lens or mirror. So the bigger the mirror, the bigger the aperture, the bigger the hole, if you will, the smaller the angle you can resolve. Because for smaller angles, you have greater diffraction. For smaller apertures, greater diffraction. For larger apertures, less diffraction. So for large angle, for a large diameter, you can resolve it better. You have a smaller angle of resolution. This is so annoying. So where this becomes really important is when you've got two stars that are really close together, like in the lower right-hand image here, you've got these two circles represent two little stars that are really close together, and you're trying to see them as two stars. Now, if they're too close together, they merge and become like one star. This image represents two stars as being viewed by a telescope aperture. This gap here represents the diameter of the aperture, which we're going to call D. And so this telescope is looking at these two stars, but the light coming from these two stars gets diffracted. Remember, the smaller the aperture, the greater the diffraction. The bigger the aperture, the less the diffraction. So instead of forming a pinpoint image of the stars, it smears out into this diffraction pattern. Now, if you've got two stars close together, those two diffraction patterns are close together. And the question is, how close can they be? And you can still tell that it's two stars and not just one. Well, if you look here at the upper image on the right-hand side, here's two stars that are so close together, their diffraction patterns have basically merged. Now up here we have the graph of the diffraction pattern. One star has a maximum here and then a minimum, and the other star has a maximum here. They're so close together that they're not resolved. They're not separated into two stars. Over on the left-hand side, we see the opposite extreme where you have two stars that are far enough apart. You can see the diffraction pattern of one is clearly different from the diffraction pattern of the other, and you can see two stars, not just one. So the question is, how close together can they be and still consider them to be resolved? Well, the central image shows the criterion of that distance. Notice that the diffraction pattern of one star has a maximum and a minimum, and the diffraction pattern of the other star has a maximum and minimum, and the criterion of having them being resolved is that if the minimum of one diffraction pattern is in the same position as the maximum of the other diffraction pattern, then we can say they're just barely resolved. And you can see here, you can just start to see that there's two stars instead of just one. So the mathematical representation of this is that if we take theta here to be the angular separation between the stars, the angular separation between the two stars, the minimum angular separation where you can actually resolve the two stars is given by this formula. 1.22 times the wavelength of light divided by the diameter of the aperture. So what this tells us is the bigger the aperture, the smaller the angle you'll be able to resolve between the two stars. So r, remember, is the distance from the telescope to the star. S is the distance between the two stars. And theta is the angle. So the one thing that wasn't mentioned in the last slide was the relationship between theta and r and s. You can see that little formula on the bottom there, s equals r theta. So in some problems, they'll just ask you, what's the minimum angle that you can resolve these two stars with a given diameter at a certain wavelength. But other problems might say, well, how far away are these two stars, or what's the minimum distance s between the two stars if they're a distance r away that they can be resolved. So the relationship there is just s equals r theta. If you know the distance and the separation between the stars, you can calculate the angle in radians, the apparent angle between the two stars, and fit that into the formula.